Hello everyone. Let's start by taking a look at the Lewis structures for these first three compounds here. We've got pH3, SiF4, and CH2O. I went in and actually underlined the central atoms for these Lewis structures, but we need to understand that if we have an atom that has a Lewis symbol where there's 3 open electrons or 4 open electrons in the case of silicon and carbon, they're most likely going to form 4 bonds and therefore be a central atom. So if we take a look at the Lewis structures, phosphorus had 5 valence electrons, hydrogen each had 1, so that's a total of 8. And in this finalized Lewis structure, we have a total of 8 valence electrons. Here we have silicon with 4, each fluorine bringing 7. So we have a total of 32, and 32 being accounted for in this Lewis structure. And then down here, things take a little bit of a change because carbon, 2 hydrogens, and oxygen are going to have this finalized Lewis structure. So again, notice carbon had 4 electrons in its Lewis symbol, 1 on each side. Therefore, it likes to form 4 bonds, 1, 2, and then 3 and 4. Okay? So if we scroll down to the remaining Lewis structures, we notice that the oxygen had 2 dots open on its Lewis symbol, so it likes to form 2 bonds, and it actually forms a single bond between the 2 oxygen atoms, and then 2 hydrogens on either end. Remember, hydrogen is a terminal atom, therefore it will not bond to another element. Well, it won't bond to 2 elements, so here it bonds to just the 1 oxygen, and that's it. Here for C2Br2, again, we have to remember that carbon likes to form 4 bonds, so carbon is actually going to triple bond with itself and then have a single bond to each bromine. Last two, very similar structures, however this is the sulfite ion, so it has the -2 charge, meaning 2 extra electrons were added into the Lewis structure, and we notice that the difference between the two is there's no longer a double bond between this sulfur and this oxygen, and therefore a lone pair was added onto the sulfur, and then another lone pair was added onto this oxygen to accommodate both elements' octet. And remember that when we calculate or when we create Lewis symbols for ions, we have to put the brackets around it and then the charge that corresponds to that overall symbol. Alright, so now that we look at the Lewis structures drawn correctly, we can determine the number of electron groups. Now remember, any lone pairs is going to represent an electron group, and any region of bonding is going to represent an electron group. So both of these Lewis structures represent 4 electron groups, therefore a tetrahedral electron geometry. Remember, tetra is the prefix for 4. Down here with CH2O, this double bond acts as 1 electron group, and these 2 single bonds act as 2 separate electron groups. So now we have 3 electron groups, or an electron geometry trigonal planar. And then for H2O2, we can determine the electron geometry based on either oxygen, because they're both going to represent the same thing, so it's on opposite sides of the molecule. And these oxygens each have 2 single bonds and 2 lone pairs. Therefore, they have 4 electron groups and, again, tetrahedral geometry. The only time we see a linear electron geometry is with C2Br2, because this carbon's triple bond acts as 1 electron group. Therefore, each carbon has only 2 electron groups and an electron geometry that is linear. And then the change from a structure without an ion to an ion actually causes the electron geometry to change as well. So this central sulfur atom has 3 electron groups, again a double bond, 2 singles. And then this one has 1, 2, 3 single bonds, and that lone pair acts as an electron group. Therefore, the electron geometry changes from trigonal planar to tetrahedral. Now, when we're determining molecular geometry, we have to compare the number of lone pairs and the number of bonding groups. Now, I understand that I made a complete mistake when I created this key, and I did the number of bonded atoms, so don't look at this and think, where is he getting 3 lone pairs? There's 3 atoms bonded to this phosphorus and 1 lone pair. Therefore, that makes it trigonal pyramid. And on the silicon, there are no lone pairs, but 4 bonding groups. Therefore, it stays the tetrahedral geometry because it had 4 electron groups, and those 4 electron groups all represent 4 bonds. Now, anytime we have 3 electron groups we're going to have a trigonal planar electron geometry, but if those 3 electron groups are all representing bonds, then it's also a trigonal planar molecular geometry. The only time we see a different molecular geometry with trigonal planar electron geometry is if one of these electron groups was a lone pair, and then we would call that bent. Similar to H2O2 and very similar to H2O, here we have 4 electron groups, but only 2 of the electron groups are bonding groups, and the other 2 are lone pairs. Therefore, this has to be a bent structure. And we can see the last 3, linear electron geometry means a linear molecular geometry. There's only one for each of those. And then here it's trigonal planar because we have 3 bonding groups. And down here it's trigonal pyramid because we have 3 bonding groups, but that one lone pair of electrons on top of the sulfur is going to deflect the other 3 bonds away and form a pyramid base. Now when we're discussing polarity, we have to first evaluate whether or not the bonds within the Lewis structure are covalent, polar covalent, or ionic. And this is where we get these numbers here, the electronegativity values. So we can see that phosphorus and hydrogen both had electronegativities of 2.1. Therefore, each bond technically has an electronegativity difference of 0. However, even though each bond is covalent, the overall molecule is polar due to the lone pair on that central phosphorus. Okay, remember, lone pairs on a central atom are pretty much going to be a good indicator that the molecule is polar because those electron groups are both negative. So their negative charge are going to deflect the other bonding groups away. Therefore, we have that pyramid base because it's trigonal pyramid, and we have a point of asymmetry cut across the phosphorus atom. Okay? Down here, we look at the electronegativity difference of silicon and fluorine, 1.8 minus 4. So we have a really huge electronegativity difference of 2.2, technically classified as an ionic bond. However, this molecule is nonpolar because the 4 bonds equal each other out. There is no plane of asymmetry within this molecule. With CH2O, we do have a plane of asymmetry. If I cut right across this carbon, like so, I have oxygen on the right and I have 2 hydrogens on the left. So even though the carbon-hydrogen bonds are only covalent and the carbon-oxygen bond is polar covalent, because there's a large area of electronegativity on the side with the oxygen, we would classify this molecule as polar. H2O2, because we have the 2 lone pairs on oxygen, we have to remember that with this bent structure, these are actually kind of angle up and away, and there's going to be a plane of asymmetry across the oxygen-oxygen single bond. Therefore, the molecule is going to be polar. With C2Br2, all of our molecules' bonds are less than 0.4. Therefore, they're all just covalent. None of them are polar covalent. We also have no point of asymmetry because this is a linear molecule. Therefore, this is going to be nonpolar. Now, the difference between sulfur trioxide and the sulfite ion really comes down to the fact that this lone pair is going to deflect these oxygen groups away and cause it to have a pyramid base. So that pyramid base causes it to have a 3D shape, and if we cut across the sulfur atom, that makes it a polar molecule. The 2 electrons that act as the top of the pyramid are deflecting it away, giving a point of asymmetry. But without the lone pair of electrons, the 3 oxygen atoms form a 120-degree bond angle across the circular or the planar structure of this molecule, and there isn't a point of asymmetry. Therefore, this is a nonpolar molecule. All right, so down below, question number 10 talks about isoelectronic species have similar electron configurations. So when we compare the electron configurations to these 2 ions to that of helium, we can see that they all get 1s2, 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 because the lithium ion has 2 electrons, the hydrogen ion has 2 electrons, and the helium atom has 2 electrons. However, we only have to do the first 2 in part B to realize that these are not isoelectronic. The calcium ion goes all the way to 3p6, and the neon atom ends at 2p6. Isoelectronic means that they have similar electron configurations. Down below, you see that there are at least the correct Lewis structure is the first one listed. So as we get all the way to 4p6, we're looking at the krypton atom, or if we get all the way to 4F10, we're looking all the way. And then at krypton 5p3, we're at antimony, and argon 4s1, we're at potassium. But we can have multiple other ions that represent these same Lewis structures as long as their charges go in the correct order. So here, argon, even though it doesn't exist with a -1 charge, if we were to give argon an extra electron, its electron configuration would look something like this. Argon without the charge, with 1 electron going into the 4s subshell. Last but not least, we have our periodic trends, and we need to remember these over here on the right. Atomic radius is the distance from the nucleus to the outermost valence electron, and those actually increase as you go left across a period and down across a group, or down a group. So fluorine is our smallest element, and francium is our largest element. Now, due to their size, ionization energy increases as you go up and as you go to the right. So the smaller an atom gets, the easier it is, or the more energy it takes to take away its valence electron. That holds true also for electronegativity. The smaller an atom is, it means that its positive nucleus core is more exposed. Therefore, electrons are going to be more attracted or gravitate more towards that particular atom. So again, fluorine has the greatest electronegativity, francium has the least electronegativity. So when we compare the answers over here, aluminum or boron, aluminum has a greater atomic radius, sodium is larger, sulfur, oxygen, and bromine are all larger, and then calcium is also larger. Make sure you have a periodic table out as you compare these correct answers, and pay attention to their placement on the table. Aluminum is larger than boron. Down here with ionization energy, we see that the pattern also holds true. If you're to the right within a period, you're going to have a greater ionization energy. And if you're higher up in a group, again, greater ionization energy. Same holds true for electronegativity. Please remember that there are some questions that I posted online through Mastering Chemistry, which is another really great resource that you can use when it comes to review for the test tonight. If at any point this video seemed a little blurry, or you needed to go back, that's the great thing about these videos is you can rewind and click back to one particular area, or pause the video if you want to copy any of these things down. Please feel free to swing by my room tomorrow morning if you have any questions. Send me an email later tonight if you're still studying and you're not sure why one of the answers was the way that it is. Hopefully I'll get the answer or the email in enough time and be able to respond as quickly as possible. Okay, hopefully this review today and the video was helpful, and Mastering Chemistry is even more helpful. Good luck, and we'll see you tomorrow. Thanks.